Hello. In this lecture, we're going to do a little bit of a review of thermodynamics and conversion of heat into work, or just conversion of energy from one form to another. We'll start with this slide right here that it shows the different types of energy sources in conversion processes. For example, shown up here at the top, we have like biomass, solar, and then solar energy is, can be directly used for heat or converted to electricity through photosynthesis. It also creates ocean thermal source and is responsible for driving various aspects of the climate, like our wind and water systems. Down on the bottom here shows some other sources in either red or orange, and I don't know, maybe that means they're bad. But anyway, so the fossil fuels are typically used as our energy source to burn for heat and use as a conversion to mechanical work. So, for example, your internal combustion engine, burns petroleum and creates mechanical work so you can move your car. Or coal-fired power plants will burn the coal to produce heat to do mechanical work to be converted to electricity. Um, Various types of energy sources will go through different processes, and we have to be able to treat them differently to figure out how much usable work we can get from the various sources. Again, the overall objective of this course is to understand a little bit more of the energy landscape and see what are the various things that we can do to develop more sustainable energy sources. And again, sustainable energy sources, we talk about those as energy that we can use without depleting them and also minimizing the effect or the impact that we have on the planet around us, on our environment. Um, and again, these various, we can use and there's probably a right way to use the different types of energy sources. So, for example, solar can be used directly as a way of heating and for thermal energy. The solar can be converted using photovoltaics or solar panels directly into electricity, which can be used by, our homes, businesses, and potentially transportation if you have electric vehicles. And then, biomass, again, burned in various ways. And, and again, depending on the type of energy that we have access to, it'll require some sort of thermodynamic treatment of of the source to look at what is our usable work or electricity that we can get from that particular type of system. So the energy source that we have access to is, again, it's not often the useful form of the energy, and we have to convert it into something else. So the type of energy that we like to use are generally things like electricity or electrical power. We like thermal energy for heating and cooling. And then also potential mechanical energy as a way for movement. And a couple of examples is we can convert flowing water into electrical power. We can convert sunlight through the, the photonic energy into electrical power. And then fossil fuels, which have potential or chemical energy, we can convert through a thermoelectric generation process. So the things that are going to be important to determine the efficiency of these energy systems, we're going to have to go back and review some of our thermodynamics. Transport and reaction kinetics are also important, but a little bit to less extent than the thermo. So thermodynamics are really going to drive our understanding of the ability to convert one form of energy, which isn't super useful to us, into another form of energy that we can use. So there are various transport processes, and these are constitutive laws to characterize different types of rates. And so when we think about transport, there's a couple things that we can think about. We have heat transfer, so moving heat through a medium into another one. We have mass transfer. So again, we have diffusion, so movement of mass from one location to another. And then also momentum transfer, and this is responsible for the Navier-Stokes equations that describe fluid flow. These types of the rates of which things move, whether it be heat or mass or momentum, are governed by a couple things. So there's going to be a driving force, and then there's going to be a resistance to that driving force. So the driving force for these rate processes can be temperature. So temperature differences are going to determine the rate at which heat can move. We have concentration gradients, and that's going to help. That's going to be a driving force for mass movement. We also have pressure gradients and then chemical potential gradients that will be responsible for things moving from one, location, one place to another. And then these rates, in addition to the driving force, there's also a resistance to the driving force. So materials will have things like thermal conductivity. So that'll tell us it's a physical constant. These are typically physical constants that for particular materials, and they can be a function of um, temperature, pressures, etc. So thermal conductivities will determine how efficient or how quickly heat can transfer through a material. The molecular diffusivities, again, how fast things can diffuse from one place to another. Same with permeabilities, and then viscosity determines is going to determine momentum transfer as it's necessary to be used to treat the Navier-Stokes equations. So just a few important chemical reactions, and we're gonna come back to these things a little bit later. So we'll see these before, but again, I think these are, just from in terms of stoichiometry, anyone who's been through a chemistry, maybe a college level chemistry class, I think we can do these types of balances. And so combustion is something that is important. And in combustion, we generally burn something to produce heat, and these are going to be exothermic reactions. So the burning of a hydrocarbon is going to be converted into CO2 and water, and then that process is going to release heat. So, for example, if we think about natural gas, so natural gas being primarily methane, and again, if we know methane, it goes to CO2 and water, we can just write out the reaction. So we have our CH4 goes to CO2 and then H2O, and then we just need to balance the atoms. And a variety of ways you can do this. I typically start with the C's, and then I go to the H's, and then I go to the O's, oxygens. If we have something like gasoline, oftentimes we approximate gasoline as isooctane. So again, we know that the hydrocarbon is going to go to CO2 and water, so we can start by balancing the carbons, and then the hydrogens, and then the oxygens at the end. And then finally, we have cellulosic biomass, and again, we can approximate this as like a cellulose or a sugar type of a molecule, and write the balances here. And again, these are going to be approximations because we're sort of coming up with this is going to be a general description or relative amounts of CH and O that exists in these. We can think about doing this for coal as well, because then coal is just going to have a different ratio of carbon, hydrogen, potentially some oxygen and sulfur and some other things. But again, these being able to write these reactions are important so we can determine, again, from these reactions, we can get the heat of reaction, we can get the amount of heat that's released per mole, and then we can start thinking about how to calculate things like, how much methane do we need to burn in order to release a certain amount of heat? So we can do that through the mass balances and our energy balances. Hydrogen production is also important, so we can get hydrogen production from either the steam reforming of methane, so that's reacting methane with water to get CO plus H2, and then after that we can do the water shift reaction, which react our carbon monoxide with water to get CO2 and H2. So again, this is an important way of that we produce a lot of hydrogen, and this is going to be necessary for both ammonia production. So then we can again do ammonia production, or potentially even fuel cells or other things that require hydrogen. Um, so in general, when we're looking at reaction rates, and again, this isn't necessarily going to show up a lot, but just a quick review of your kinetics background. And typically we can express reaction rates as a rate of change. So the rate of change of concentration with respect to time. So again, the either the consumption of a reactant or the production of a product, so that would be the rate of change of a concentration, is equal to or proportional to some sort of stoichiometric coefficient, reaction rate constant, and concentration of chemical species raised to a specific reaction order. Um, and again, in these terms, C is the concentration, N is the stoichiometric coefficient. A is going to be like the alpha is going to be the reaction order or the power of the concentration. And then we have a specific rate constant K. And again, from kinetics in the Arrhenius law, hopefully you are familiar with the reaction rate constant is equal to some sort of a frequency factor times an exponent that's a function of temperature. So reaction rates, a strong function of temperature, where this term EA is the activation energy and T is temperature. Along these lines, a lot of times I think you can think about reactions in terms of either elementary reaction, and if you're not familiar with that means, this is a good time to review it. Reaction rates can be described in terms of a particular order. So we might know the reaction is first order with respect to reactant A, and based on that information, we can come up with descriptions for the reaction rate term. So maybe brush up those. If you know zero order reaction, first order, second order reaction, and then reactions can be different orders with respect to different reactants. So like we noted, the heat can be released, or thermal energy can be released or absorbed by chemical reactions. So if it's exothermic, that means heat will be released and the change in enthalpy of the reaction will be less than zero. Or if the reaction is exothermic, that means the reaction is going to absorb energy from the surroundings and the delta H of the reaction will be greater than zero. Some reactions can be defined to be reversible or irreversible. So an irreversible reaction will only go forward. A reversible reaction can go forward and in reverse. And these reversible reactions are sometimes limited by chemical equilibrium. And some equilibria favor, your desired products where others might not. Other important aspects of chemical reactions is you have the use of catalysts, and catalysts can accelerate the rates of reactions while not affecting the chemical equilibrium. And then oftentimes in catalyst type reactions, these can be mass transfer limited, such that really the rate of reaction is more so defined as the mass transfer of the reactants or the products through the catalyst type material. Again, we need to be familiar with our chemical kinetics, but again, just to review and touch on these basics is about what we need for this class. All right, so we've just touched on transport and touched on kinetics, and I think the rest of our time here, we're going to talk about thermodynamics and efficiency. And so now in terms of thermodynamics or efficiency, again, when we define efficiency, we need to be specific in terms of how we define it. We can have a series of processes that have various efficiencies, and we can talk about the individual efficiency of one process, or we can talk about an overall efficiency of the whole process. And you can kind of think about this with respect to, if we want to do a comparison between, let's say, electric vehicles and internal combustion engine vehicles, right? So for an internal combustion vehicle, if we just really start from the fuel, which is the petroleum, the internal combustion engine is going to have a specific efficiency that's related to the engine process, and that's probably on the order of maybe 20 to 30% efficient. I also have efficiencies in terms of what friction and other components along the car. But I mean, in general, you have your fuel, and then if we think about things like electric vehicles might have a different type of efficiency. So the electric vehicles will have an efficiency associated with charging the battery. So if you take we sort of assume that all of the things like friction on the road, the aerodynamics, all those things are equal, and we just look at the power source. So again, for the battery, we have a maybe charging efficiency, so we might lose some power there. But then we have to get that electricity somewhere, and there's going to be an efficiency from the original energy source for producing that in the first place. And so there we might have a charging efficiency of, let's call it 95%, but then the electricity generation might have an efficiency from its original energy source of 30 or 40%. So when we compare the overall efficiencies, we have to look at every process along the chain starting from the original source. And so that's what we'll do in this class a little bit as we're looking at the different processes. But ultimately, if we can get the individual efficiencies, we can get the efficiency of the whole energy chain. All right, we need to know or familiarize ourselves, or we use the rules or the laws of thermodynamics, and we don't necessarily speak about it when we do it, but when we talk about the first law, we have energy that's conserved. So we have our energy balance. So anytime we write an energy balance on a process, we're using the first law. We'll do that coming up. The second law talks about irreversibility and entropy generation. So what that means is energy tends to move from order to disorder. So at worst, entropy won't change. At best, entropy will continue to increase. And then we have the concepts of max and min work. So again, we'll look at some of these as we treat different energy sources. We have a really important thing for many topics in this class is going to be the power generation via heat to work cycles. And these are our thermoelectric energy generation process. So the main ones here, I mean, we have from your physics class, you probably heard of the Carnot cycle. So we'll talk about the Carnot cycle, and we'll use that to lead into talking about the Rankine process, which use steam primarily or other fluids as the cycle or the movers, as they say. Or we'll talk about the Brayton cycle, again, another common heat to work system, and then also combined cycles. So we'll see more of this coming up. So for these different processes, like I mean, maybe not except for the Carnot cycle or for the Rankine process. In some of these other heat to work processes, we use the phases of matter. So every material will go through, or the different, let's say we can talk about it with respect to water, but water or other compounds will have a thermodynamic phase diagram. And what that means is it tells you where the species exists as a liquid, where it exists as a vapor, and where it exists as a solid. And the important entrance or the important prop or these phase diagrams are constructed with respect to pressure, temperature, and then also specific volume. Okay, if we take a cross section of these and we just look at it in terms of pressure and temperature, this is a typical phase diagram that we're used to looking at for a given species. And particularly we see this for water, and I think this example right here shows us for water. So for these phase diagrams, we know at what points do we have vapor. So again, if we have high temperature, at high temperature, we have a vapor over a range of pressures. As we decrease the temperature, the vapor will condense and we'll get a liquid. But there's a point there's an area of temperature and pressures. There's a set of temperatures and pressures at which we can have water exist simultaneously as a liquid and as a vapor. And that also depends on the specific volume. So if you think about taking water at a certain temperature and pressure and confining it to a certain container size, and then let's just say you increase or decrease the container size, you might vaporize some of the water or condense some of the water. So you just have a different amount of you have a different amount of water versus vapor depending on the size of the container at different temperatures and pressures. And that sort of describes what this specific volume element of it is. So in any case, so we know and the conditions to which water can be a vapor, which water will be a liquid, and then the conditions over which we can have both liquid and vapor exist in equilibrium. I mean, we know one of those already. So one of the conditions at water can exist as a vapor and a liquid is like the boiling point, 100 degrees C. We can have water as a liquid or water as a vapor. And then the various, or there are many other, uh, there are many other points along this vapor liquid equilibrium curve. And then this right here is called the phase envelope. So we have our on one side we have what would be saturated liquid. On the other side we have saturated vapor, and then in the middle we would have vapor liquid in equilibrium. And then as we go to the right side, this would be considered a superheated vapor. And then as we go to the left side of the liquid, that would be a subcooled liquid anywhere in this region. And if we continue to cool it, we'll eventually get to our solid liquid line, and then we just have our solid, for example, ice in the case of water. So in the power generation cycle, particularly the Rankine cycle, we use we we take advantage of the incompressibility of water and the high energy of a high temperature, high pressure steam. Okay, so first let's go through the Carnot cycle. And you may have seen this a while back, or at least in your thermal class, also in your physics class. But this is a hypothetical cycle that's based on an ideal gas. And in this process, it shows us how we can convert heat into work. So we can take heat from a hot reservoir, and we can get usable work out of that, and then we can transfer or reject um, the the unusable heat to a cold source, and then can repeat that cycle. So in general, when we think about the Carnot engine, what we have right here is we have a piston, and this is going to be a frictionless piston. Okay, so there's no lost work associated with this. And so if you imagine in the piston, there's an ideal gas. So it's an ideal gas, so we know how to describe its temperature, pressure, volume relationship. So in the first part of the process is we go through what's called isothermal heating. And so when we take this gas and we put it in contact with a hot reservoir, the that's at a constant temperature, the piston will expand um, while the gas is heated up. Once when we remove once we remove the once we remove the cylinder from the reservoir, and we insulate it again in these conditions right here, the pressure at the higher temperature of the gas is going to be higher than the pressure on the outside, so the piston's going to continue to move until the pressures are equal. um, And then next, what we do is we take this cylinder and we put it in contact with a cold reservoir, and this could be ambient, for example. So again, the hot reservoir could have our heating source, and the cold reservoir could be like an ambient temperature. And when we put this in contact with the ambient temperature, what happens is the the process that the system will cool as it rejects energy to or the system will compress as the gas is cooled and rejects energy to the environment. And then again, once we remove that, the pressure inside the system is lower than the pressure on the outside. So the piston will continue to compress until it reaches the same temperature and pressure. And then we can take this and we can heat it back up, and we can go through this cycle again. So one of the ways that we can represent or we can describe from these cycles, we can generate a net positive amount of work. So the net positive amount of work that we get is we get the work that's associated with this expansion. So we have heating that causes the cylinder to move up, and it does work on the environment. So that creates a positive work. And then on the cooling, we're contracting, so we're actually doing work on the system. So this is a net negative component. And based on the temperatures and pressures, but based on the differences in the hot temperature and the cold temperature, um, we can produce an amount of usable work from this cycle. And so these cycles can be expressed in a couple of ways. So we have a pressure volume diagram, we have a temperature entropy diagram, and then also we have a pressure enthalpy diagram, which will be useful, and we'll come back to that a little bit later. So if we kind of work through these processes, we can, we can see all of the we can work through these on the pressure volume or the temperature enthalpy depending on what necessarily what we're trying to do. And they're both useful to identify starting and stopping states, because in some cases we have isothermal, which is constant temperature, and in some cases we have constant entropy because it's irreversible. And when there's no, in the case of adiabatic, when there's no heating and cooling and it's frictionless, then we have constant entropy processes. So these TS diagrams are useful to work through these cycles. And then also the PV diagrams are useful to calculate the amount of work that we can get based on the heating and cooling. Because we know that work, expansion contraction work is, delta PV. So we have our pressure versus volume. So we can see the net work from the isothermal expansion part. And this says combustion here because if you could imagine we had a combustion process as our heating source, for example, like an internal combustion engine, but it doesn't necessarily have to be um, combustion. But in any case, so this would be for like an engine, for example. So we have our combustion, which heats the gas, and while we heat the gas, the pressure decreases as the gas expands. So this shows increase volume, decrease pressure as this system expands from the added heat to the process. Um, and then after we remove the heating, we get the power stroke part, or the adiabatic component. And the adiabatic component is where the piston just keeps moving until there's an equal pressure from inside and outside. And then once we do the cooling, and this would be like releasing the exhaust to the environment. Once we let out the hot air and the system cools, we have this sort of this isothermal compression part of it, and then this is the amount of work that's required. So we are compressing it. So decrease volume, increase pressure right here. So we would be adding work into the process, and then just finishing up the final compression stroke as the system is isolated as we remove the cooling from the process. So from here, the integral of PV on the top curve is going to be our our positive work, and then the integral from PV on the compression side is going to be our the work that we're doing on the system. So if we integrate in this area, we can get the usable work that can be accomplished through this process. So we can also use our energy balances on all of these different things too. So if we think about the different steps of the process, our isothermal expansion part, again, remember our energy balance is what? I think the designation that they're using here is going to be delta U equals Q minus W, and it defines work as work that's being done by the system. So in here, so for our isothermal expansion, and that's just to keep sort of the work, that's just to keep things, the terminology positive. So this W is work that's done by the system. So in the isothermal expansion, delta U is 0. So we just have 0 equals Q minus W. And so in this case right here, we have delta Q equals the work. And then we can get this, we might need to be able to determine one of these things, but we can calculate the delta W based on the change in pressure and volume of the system. Okay, then when we have our adiabatic expansion, again, so this is, in this case right here, we have Q equals 0. So we have delta U equals delta W. And again, we can potentially get, either one of these, or we might have to have a relationship between the two, because we know for a gas how to calculate delta U. I think it's something like, CV delta T. So that based on the change in temperature during the adiabatic expansion. So how much does the temperature of the gas change while it continues to while it continues to expand without heat transfer. So as it expands, the gas is going to cool down a little bit. And then the next two processes are sort of the same as the previous ones, just on the compression side. So it's going to be a negative work due to cooling, or due to the temperature, as the temperature of the gas rises as it leaves leaves the system. So the Carnot efficiency, we can calculate that. The efficiency is generally defined to be the energy out divided by the energy in, and we can get the energy out, which is the usable work, versus the energy in, which is how much heating that we're doing on the system. And we don't necessarily we don't take the net Q. We just take the Q required to do heating, because this QC, the cooling process on this, is generally cooling that's just the cooling is done by the ambient. So whatever we have, whatever cold reservoir we have access to, we're not doing any work to get that Q. That's just going to be the environment. The Q heat is where we actually put into the system. And so by using the first and second law, we can show in general the energy out is, again, Q in minus Q out over Q, or we can, substitute terms around, and we can see that for a Carnot engine, it's going to be the efficiency is going to be T hot minus T cold over T hot. And what's important to know? What are the units that you need to use on these? Can you use Celsius, or can you use Fahrenheit, or rank? What is it? What are the units? Kelvin or Rankine? I don't know. I'm not sure. Well, I think you know the answer to that. And I'm asking the question because in this case right here, we just need to use absolute units. So absolute measurements of temperature like Kelvin or Rankine. This right here shows let's see, it shows the TS diagram for a Carnot cycle that would use a fluid. One of the challenges with the Carnot cycle with a fluid is what you can see is that in one state we have a saturated liquid, in another state we have a saturated vapor. And then we have a vapor liquid equilibrium. So we have two states existing at these two locations. And one of the problems with application of this is that it's extremely difficult to design systems that can handle the liquid and the vapor at the same time without degrading or corroding very quickly. We can talk about Carnot cycles from the standpoint of, what was it? We were converting heat into work. So we wanted to take a heating source and use that heating source to produce usable work. Another thing that we can do with the Carnot cycle is we can go in the opposite direction. So we can do work to move heat. So heat will spontaneously move from hot to cold. So if we want to move heat from cold to hot, we need to put work into it. So an example of that would be like your refrigerator. We put work into the refrigerator in the terms of compressors in order to move heat from the inside of the refrigerator, which is cold, to outside the refrigerator, which is hot. And in this case, we just go in the reverse direction. So here's an example of a TS diagram. We'll come back to this later when we do heat pumps and refrigeration and some other things later on. Okay, so here's our TS diagram, and then we also have this is a pH diagram. So again, in this process, we have our, what is it? We have a heater, a compressor. We have a heater, a compressor, a cooler, and a throttle. And again, remember it's important to remember on these diagrams is this line right here is our vapor liquid equilibrium curve. On the inside, we have vapor and liquid. On the outside, we have only liquid or only vapor. Let's see. So let's see where we go. Okay. So now let's look at during these in the processes of vapor compression. We'll start with this step right here. So wherever we are here. So this doesn't quite align with this figure. Well, just follow me here. So we start with a compressor. So we take a um, we take like a mostly a vapor, and we compress it to a high temperature, sort of higher pressure, high temperature, high pressure. So we take we compress a vapor to high temperature, high pressure, and then that um, that vapor will go through a cooler. So what happens is that as that vapor goes through a cooler, it's going to absorb heat from the environment as as it condenses to a saturated, or as it condenses to a liquid. So so this let's see. So again, we'll think about what this is. What are we saying cooler? Just to be clear. So think about your refrigerator. We compress it. We have this hot, high temperature, high pressure fluid. Then we take this fluid and we send it through the coils on the outside of the refrigerator. So the ambient is going to take heat from that high temperature, high pressure fluid, and it's going to cool that heat. So the hot the heat is going to give, or the hot fluid is going to give off heat to the ambient, and that's why the back of your refrigerator will be hot, and it'll give that off until it gets to a saturated liquid. So it's going to condense in that um, in that condenser, or the back of the refrigerator where it's still hot. And so now we have this hot liquid, and we take this hot liquid and we send it through a throttle. What happens when a liquid goes through a throttle, it'll expand and some of it will vaporize. And the vaporization of some of the liquid causes a quick temperature drop. So this liquid, some of the liquid will vaporize and dropping the pressure, or dropping the temperature. And so now we have we have a vapor liquid equilibrium that's at a significantly lower temperature, because again, we took this saturated liquid and we allowed it to expand. Um, and Yeah, we allowed it to expand, where the only thing that could happen to it was vaporized liquid, and that accompanied with a temperature drop. And now we have this very low temperature, or a much lower temperature, and this will be the temperature that's flowing on the inside of the refrigerator. So this lower temperature will now pull heat out of the refrigerator, so that the fluid is getting heated by the refrigerators. The refrigerator is being cold because it's transferring heat to the fluid, which is becoming vaporized to to close to a saturated vapor. So that's the compression cycle. And again, we can look at this also on the pH diagram. So again, this is a pH diagram. Here is the phase envelope. On the left side, we have our liquid. On the right side, we have our vapor. And again, we can kind of go through the same process. If we start from what's entering the compressor on the pH diagram, we can follow. Again, there's going to be the nice thing, the TS diagrams and the pH diagrams work well together. Um, Again, on the compressor, what do we have going in the compressor? We have a constant entropy. So what we can do is, starting from a saturated vapor on a pH diagram, we can follow the constant entropy lines until we get to our until we get to our the temperature that we compress the gas to, or the pressure. I mean, we might know the pressure, we might know the temperature. That's something that we can sort of pick in terms of how we operate the system. And then, so we compress it to there, and then in the cooler, we undergo a constant pressure process. We have constant pressure cooling, and it's going to cool all the way down until it gets to a saturated liquid. So again, we know where we're going to be on the outlet side of the system. And then again, the expansion. So if we assume a delta H of 0 through a throttle, the expansion part's going to be straight down. So delta H is 0 on that part. And then again, evaporation, this is going to be constant pressure at the low pressure side, while the liquid evaporates to a saturated vapor. coming out. And because this is a pH diagram, now we know how much heat is added here. It's just delta H. How much heat is removed? It's just delta H. How much work is done by the compressor? It's just delta H. So these pH diagrams are extremely helpful for us to calculate how much heat, how much work from these cycle processes. Um, let's see, a few notes here. I think we sort of summarized these a little bit already. We said that, heat only flows from hot to cold. So we can use the flow of heat from hot to cold to generate work. That's the Carnot cycle, Rankine cycle. Any first system free of external influences become more disordered with time, and this is described by entropy. Let's see, heat engines, we can't convert are not capable of converting all of the heat into useful work. So again, and the reason for that is some of the heat has to be rejected to the environment. If we had access to a cold sink or an environment that had 0 Kelvin, then potentially we can. But we know that that's not necessarily, that's not a real thing. We would actually have to do work in order to get close to that system. And again, so let's see. So the thermal bottle, like there's a thermal bottleneck that constrains devices that convert potential energy to heat, and then use that heat to convert to work. So again, so we have thermodynamic limitations in converting or in converting potential or chemical energy into heat, and then we can also convert that heat into usable work. So we have a couple different efficiencies that come into play that we have to consider for these processes. All right, so let's move on now to the Rankine cycle. Again, Rankine cycle, this is going to be very similar to the it's similar to the Carnot cycle, but what instead of using an ideal gas, we're going to use water. Um, so just to quickly, maybe to describe this, it's most convenient to just work through the Rankine cycle process. Remember, by being a cycle, what that means is we're talking about the fluid that's inside the cycle. So the fluid is going to undergo these changes in state, and based on the changes in state of this fluid, we can get usable work out of this fluid. But the fluid it's like a closed system that stays in a cycle. So let's see what happens first. So we're going to start with superheated steam is generated in a boil. So that would be this right here. So state 2 to state 3. So we start from, in this case right here, it would be high pressure liquid. And when we heat up high pressure liquid, we get high temperature, high pressure steam. Um, and then this high temperature, high pressure steam is expanded in a steam turbine. And as this high temperature, high pressure steam is expanded into the turbine, it rotates the turbine and produces usable work. The coming out of the turbine is going to be a low temperature, low pressure, but again, it's still going to be steam. So this is going to be vapor, this is going to be vapor, this is going to be liquid. The low temperature, low pressure steam is going to be condensed in a condenser and converted into saturated liquid or potentially cooled liquid, but generally like a saturated liquid. And then this saturated liquid is is pumped. So I'm not going to say compressed. It's incompressible, but the pressure of the liquid is increased by using a pump. So we do work on the process by a pump. And so because it's incompressible, it takes very little amount of work in order to pressurize the liquid from like what is it, from like a low pressure, like an atmospheric pressure, up to something that's, significantly higher pressure. The reason why this change of state is really important is because if we didn't condense this liquid, right, if we didn't condense this low temperature, low pressure steam back to a liquid, and instead we just tried to compress it, it would require a significant amount of work to compress a vapor. By condensing it and getting rid of that unusable heat, again, we're rejecting, that's the unusable heat that we have, and then we're using a pump to compress it. We do very minimal amount of work in order to compress it. And then we get a lot of work out by expanding the high temperature, high pressure vapor through the turbine. Um, let's see. So so some of the things to kind of consider is oftentimes this coming out, if it's a saturated liquid coming out, there's a risk of having water and vapor in the turbine system, and that's just not great because that'll wear out the and corrode the the blades of the turbine. Here's another pictorial representation of the Rankine cycle, and we'll work through these on the pH diagram as well. So we can kind of see this looks a little bit like a power plant. You can see the water stacks over here. You can see here is the heater place. And so this heating part of it, maybe what are we using coal here? Maybe there's coal that's being delivered into the process and the coal is being burned, and there's water that flows through here and produces high temperature, high pressure steam. The steam is run through the turbine process. Um, and then the steam or the turbine is going to rotate, and the steam is going to be expanded through these turbines, which rotates the generator that's going to produce electricity, and then the low temperature, low pressure steam is condensed by water that's coming from a nearby lake, and then the vapor or the water vapor from that absorbing that heat can be released to the environment. Again, mostly what you see coming out of these stacks is going to be water vapor. And then the saturated liquid here is going to be compressed to a high pressure. And again, gets boiled to high temperature, high pressure, and it goes through the process. And so here's a process diagram of the same type of a system. So this is example of using the Rankine cycle as part of an electric power plant. All right, so let's look at this on our TS diagram. So again, here's what we show here. We have our heating source, we have our condenser to the lake, for example. We have our pump, and then we have our turbine, which is rotating the generator to produce electricity. So where do we can start on here? We can start on the pump side. So the coming out of the condenser is a saturated liquid. So what we do with the saturated liquid is we just pump it. So by pumping it, as long as the efficiency of the pump is really high, that's a delta S is 0 or just a small delta S process. So this line right here, it can't go this way because entropy can't be decreased. It could either go slightly to the right, depending on the efficiency, or it can go straight up. So we increase it. We increase the pressure, which only slightly increases the temperature um, of that liquid. So again, pumping it, making a subcooled liquid. The next part of the process, so we have this subcooled liquid, and now we add heat to that process. So what we need to follow is we need to follow a constant pressure line. Again, um, because we have the subcooled liquid, the subcooled liquid is first going to increase temperature as it gets heated until it gets to the saturated liquid, and then it's going to stay at a constant pressure constant pressure, constant temperature as we go through this vapor liquid equilibrium. And then once it's all saturated vapor and we continue to apply heating to it, that's when we make it superheated. So again, we start from subcooled, increase the temperature at constant pressure till we get saturated liquid, and then we vaporize all of the liquid at a constant temperature, constant pressure process until it's saturated vapor, and then it comes out as a superheated vapor coming out of here. And then when we send the superheated vapor through this turbine, again, this is high temperature, high pressure, assuming the turbine is 100% efficient, we have delta S equals 0. It's going to drop straight down. Now, if there's an efficiency, we could just move this line to the right based on what the efficiency is. And we'll see that. We'll look at that later in an example. Okay, so now once coming out of the turbine is going to be nearly saturated vapor, and then that saturated vapor is going to be condensed. So we take the saturated vapor, condense it down to a saturated liquid, just convert all of the vapor to a liquid at the same temperature and pressure. So if we compare these two processes, The Carnot cycle, it's rarely used because the fluid would have to exist as a liquid vapor mixture. So the Carnot cycle would only work inside this vapor liquid envelope for us, um, for whatever the working fluid is in that process. The Rankine cycle, again, it's very similar to the it's similar to the Carnot cycle. I mean, we almost have a little square right here, but we modify it. It's modified a little bit so that we only have to work with a single phase. So again, we condense everything to a liquid and then we pump a single phase. We heat everything all the way from the subcooled to the superheated so that we're only working with a single phase coming out, and then we drive it through a turbine. So we have vapor, only vapor goes through the turbine, and then coming out is saturated vapor, and then we condense it. Okay, so we have our heating and cooling processes, and then the work is being done only on a single fluid. This is most commonly used in electrical power from fossil fuels or nuclear. So coal plants, nuclear power plants. So for the Rankine efficiency, we can get it based on the, as we showed earlier, work out, so the net work. So this would be the work out minus the work in over the Q into the system. So this is the energy that we pay for. From the first law of thermodynamics, we can kind of get that. We can get the net work out is going to be Q in minus Q out. And so the overall efficiency of the system, we can treat that with respect to the Q's, or we can also simplify it from our pH diagrams, and we can discuss it in terms of the enthalpies um, at the different states in the system. And again, the nice thing about for the case of water is we have access to charts that give us all of the enthalpies that we would need at any temperature and pressure point along the process. So kind of like what we did, and I'm probably maybe go through this a little bit quickly, but we can go through all of the states of the Rankine cycle. I don't know if it's terribly useful. It's similar to before, so I'll touch on a couple of them. And um, let's see. So when we talk about, let's see, what state are we talking about here? States 1 to 2. So the pressure change is adiabatic, so no heat transfer, and internal reversible. So an isoentropic process. So the first law for an isentropic process, Q is 0. We have work just equals m times delta H. So what is it? This is the work where we're putting work in using the pump to go from a low temperature or from a saturated liquid to a pressurized liquid. And so typical of the working fluid is assumed to be incompressible, and the mechanical power required by the pump, it can be calculated by the integral of V delta P. So the work required is going to be this, what is it? This, so kind of like the density of the liquid or the specific volume of the liquid times the temperature difference. So it's just a V delta P calculation. Pretty straightforward because it's incompressible. Okay, when we look at state 2, this is going to be our heating process. So we're taking this subcooled liquid and we're heating it to a superheated vapor. So the working fluid leaving the pump as the compressed liquid passes through a series of heat exchangers. We have a boiler and a superheater. For this process, again, we can write our first law, which is, again, what is it? For a closed system, we have Q minus W equals M times this term right here is our energy term. We're assuming kinetic energy is negligible, potential energy is negligible, little negligible. And we always do that for these processes. And those terms are generally going to be small. So in this case right here, we have the heat in is going to be this mass flow rate times delta H. So by knowing the initial temperature and pressure of the liquid and the final temperature and pressure of the vapor, those are measurable and kind of process defined things, we can determine how much heating is required based on the flow of liquid between the two states. Uh, so, and then the other two let's see, oh, this one is a little bit out of place, but let me see. Let's go here first. So the working fluid is again expanded through the turbine, and again we're ignoring potential energy changes. And the turbine's assumed to be adiabatic, so we just have work equals the flow rate through times the change in enthalpy. And again, the enthalpy entering is going to be a superheated steam. The enthalpy exiting will probably be like a saturated steam. And again, knowing the temperature and pressure, we can get the enthalpy here. So straightforward to get the amount of work coming out of this process. And then the amount of cooling that's done. And again, this term doesn't matter really because we're going from the vapor, we're going from the saturated vapor to the saturated liquid. But we can just see how much cooling is required in order to condense this stream. And this is only useful to determine what size, how big of the condenser it needs to be, what are the conditions of that component. This slide right here summarizes all of the assumptions and the equations used to calculate work and heat at different points of the process. So steam generator, this will allow us to calculate our Q. So this is the Q, this is the work that we did on the process. And then the net work is going to be the work from the turbine minus the work from the pump. So we can get our efficiency as the net work divided by the heating that's done in the steam generator. Um, all right, so this here says, do we really need to reject the energy from states 4 to state 1? So do we need to take that low temperature, low pressure steam and actually condense it? Um, yeah, and that's because of what I talked about earlier in that it is um, we can't generate net mechanical power without condensing the to a liquid because the amount of work required to increase the pressure of a liquid is significantly less than the amount of work required to increase the pressure of a superheated or of a saturated vapor. Here's the pH diagram of the Rankine cycle. And this is probably, these are going to be the most useful. And I'll work through this and I'll show you, and then we'll see one on the next slide as well for water. So again, we have pressure, we have enthalpy. Again, we have our phase envelope here. Again, we have vapor on this side, we have liquid on this side. So if we start our process where we have our saturated vapor, right, we have our saturated vapor that comes out of the turbine and is condensed to a saturated liquid. So this is where our cooling part is occurring. So we can just follow this line, again, constant pressure. It's going to be constant pressure condensation from a saturated vapor to a saturated liquid. And then our pump is going to take that saturated liquid. And again, um, the we can, based on the change in pressure that we want, we can calculate what's the change in enthalpy required for that. So that's just going to be a V delta P, and we can look up the specific volume of water or fluid at those conditions. And this change in pressure might be a specified pressure, operational pressure that we want to operate our system. So we can work over whatever pressure that we want depending on instrument or systems limitations. Again, any higher pressure is typically better. So again, we pressurize the liquid, and now this is going to be a subcooled liquid. And this line will probably be tilted slightly to the right because we have to put work into um, compressing or into increasing the pressure of the liquid. And then the subcooled liquid is going to go through a heater or a boiler. And so the boiler is going to raise the temperature. So this is going to be an increased temperature from here to here, but constant pressure, and then still a liquid. And then the liquid is going to be boiled at this constant pressure until it gets to a saturated vapor. And then the saturated vapor is going to be further heated at constant pressure. So again, this is going to be a significantly higher temperature than what this equilibrium temperature is. And then what? Then we go through the turbine. So we take the high temperature, high pressure steam and we go through the turbine. We follow a constant entropy line. So this right here, there will be a constant entropy line that we can follow to the saturated liquid. And then if there is an efficiency, so let's just say the system is 90% efficient, right? We don't actually get out, we might not get out all of this work, but we would get out a whatever, a fraction of the percentage of that work. All right, so let's look at this. I mean, this is looks a little bit messy. There's a lot here, but what we can see on here is we have our enthalpy lines going straight up, our pressure lines coming across here. You can see this is a logarithmic scale. Here's our saturated liquid side, here's our saturated vapor side, and then we have various other lines going through here. Let's see. So we have these green lines right here are going to be our constant entropy lines. So let's just say we have a saturated liquid. Let's just say at somewhere around here. Let's say we're operating at, let's say, about 15 psi absolute. So that's about 1 atmosphere. Well, yeah, we would be. No, maybe we can say we're lower than that. But anyways, we're operating here. Let's just say we compress our liquid, figure out how much change in pressure, how much enthalpy is needed, and then we send this through a boiler. We go all the way across here at constant temperature and come out. And then again, as we come out here, we get superheated. So we can see these are our temperature lines, these blue lines, or these, what is it, aqua? I think it's blue. So we can see what the final temperature coming in. So we're heating coming out here. And let's say we heat it up to this point, and then we send it through our turbine. We would follow the constant S lines down to the saturated vapor, and that would tell us what we would get out of it. Now we can work with we can sort of adjust the temperature and pressures that we want to operate. So those will be sort of design considerations, and then we can calculate how much work would we get out if we were operating over this temperature and pressure range. And then also we can calculate how much heating is required in order to get us to this, how much heating is required um, to go through this process. So we'll need to use these for some things, some activities in this class. So um, yeah, we'll maybe work through that. We can also do a Rankine cycle that has like a reheat process. So Rankine cycle, and again, these Rankine cycle there's various different configurations that these are done, and all of it is to increase the amount of work that we can get out based on from the amount of heat that we put into the process. And Rankine cycle with reheat is again, you take just looking at it on the TS diagram, we can see again, we get our superheated steam. This is what enters the turbine. So we might take that superheated steam and we might take, okay, we have the superheated steam, we run it through a turbine, and then we take the exhaust of the turbine and we reheat it. So instead of letting it go back down to a saturated liquid right here and then condensing it, we just take this and we reheat it again. And so the amount of heat that we have to put in here is going to be relatively small based on the amount of additional work we can get out of it. And so we can have a multiple, reheat type process. Um, but again, there will be some limitations. Again, this is working through some of the same calculations with reheat. Okay, so the Rankine cycle is the most important cycle. The Brayton cycle it's also very important, and a lot of processes are run using the Brayton cycle. And there's a couple differences. It is going to be similar in that we add heat, we compress, we heat, we expand. So those types of things are going to be the same. But for the Rankine cycle, this is a closed system. So we have our fluid stays in the cycle. So the water for the Rankine cycle, it it doesn't where you always have the same water that's flowing through the cycle. So you're having a change of state of a working fluid that's going through a process. The Brayton cycle is not going to be it's going to be an open system, and it'll operate the same, but just there's a couple aspects of it that are a little bit different. So here's the TS diagram. I'm not going to go through this yet, but we'll first talk about what the Brayton cycle, how it works. And we can do that based on this little figure right here. So the way the Brayton cycle works is we take fresh air and compress it. So we take air, let's say, and again, this would be sort of relatively cool air, and we compress it. And what happens when we compress it? It both increases the temperature and increases the pressure. So we do work to compress it. And then what we do is we then, with this higher temperature, higher pressure, mostly we care about the high pressure, we add some sort of fuel. And again, this could be like, gasoline or could be jet fuel. And we combust the fuel, which is essentially it heats up the gas, right? So now we have this high pressure vapor, and we combust fuel to make it high temperature, high pressure vapor. So now we have this high temperature, high pressure gas, and this high temperature, high pressure gas is going to go into a turbine where it's expanded, and the exhaust from the turbine is going to be so it expands to the ambient or to the surrounding pressure. So again, we take low temperature, fresh air at a low pressure, increase the pressure, increase the temperature a little bit, use reactive fuel to greatly increase the temperature, and then that high temperature, high pressure gas is expanded through a turbine to the, it's expanded to the low pressure. And so this comes out at a lower temperature, lower pressure, but it's hotter than the air. And so this exhaust gas just sort of diffuses into the environment. So the cooling process is not necessarily a really cooling process, but we just take the cold air and we get in the cold air, but then the hot air exhaust just sort of diffuses and cools off in the environment. And so we don't really need to worry about this, cooling or rejecting heat part of the process, which would be this step right here. So we have the compression part, we have the heating part, constant pressure, and then we have the expansion part. So the way this generally works is we get a lot more work out of the turbine than we have to put into the compressor. And with having these on the same shaft, we get a net positive work out of the turbine. And we can look at the efficiency of the Brayton cycle. It's defined here, and it comes from generally approximated from ideal gas type calculations. Here's another pictorial representation of the Brayton cycle, and here's what it might look like in terms of an engine. So here we might have cool air coming in. The cool air is compressed. We have a combustion chamber. Maybe we're burning natural gas. The combustion chamber makes it hot. That hot vapor is expanded through a turbine, and the exhaust vapors come out. And the rotation of this shaft based on the expansion. So the expansion of this high temperature, high pressure vapor rotates the shaft. Some of that work is used for the compression side, and then the rest of that work is results in electric generation. Again, gas turbines go through the same thing we can kind of look at here. So generally there's some kind of a series of turbines in terms of compressors. Here's our combustion chamber, then the vapor is expanded and comes out as the exhaust. So Brayton cycle it's common for gas turbines. So here's an example of a gas turbine to generate electricity. It's used a lot. It's used a lot with airplanes. So turboprop planes, the the compression and then the expansion of the gas will be used to spin the props. We have turbofans, these are the large commercial jets. Again, these will operate with the Brayton cycle. Turbojet engines are slightly different. They use a similar process, but they convert the internal energy into kinetic energy using a nozzle, and that's what generates the thrust. And then maybe many tanks and ships can use these types of Brayton cycle processes to propel that machinery. I think this is the last one. The Stirling cycle is the last type of engine. It's important. It's not as important. I might let you look this one up a little bit. I think if you go, it's kind of tough to explain. We have heating and cooling of a gas, and the heating and cooling of the gas. combined with how it's situated on the axis or on the shaft of the engine. Um, what are we saying? Yeah. Okay. Well, anyway, what I'm saying here, like if this YouTube video is like a minute and a half long. It shows schematically very well how the Stirling cycle works, and I think that would be maybe the most useful place to start. But otherwise, in terms of in general for the Stirling cycle, you have two piston cylinder arrangements, and the piston cylinder arrangements move. And again, it's fairly similar to the Rankine cycle, but the movement of the gases result in the rotation of the axis. And so, just in general, I think we have one piston cylinder arrangement is going to absorb gas while the other, and it's going to expand while the other one does not move. Um, the other one is going to it's going to expand, and then the gas is going to move. So after this expands, the gas is going to move from one side to the other. So then this piston is gonna compress while this piston's is expanding, and then this piston is going to remain stationary while this piston rejects the heat to the cold side. And the rejection of the heat to the cold side is going to cause this piston to move back down. And then as this piston moves back down, the gas is gonna move and it's gonna force this piston to move up. And then this is gonna again continue to expand as it absorbs heat, and it's just gonna sort of repeat through this cycle. I don't know if I think if you watch a schematic of it, that general process makes sense. But we can treat each of these individual steps similarly like we did before. But again, we have now it's a little bit trickier because we have multiple different compartments. And so we can think about, this next slide will sort of go through and look at some of the individual processes that are occurring. And so in one case, so the hot cylinder, so the gas is expanded on the hot cylinder side, and then most of the gas that's located over here. Um, so the rotation of this axis will have a movement around it. So this gas is expanding. Most of the gas is over here, and as it compresses, it moves the hot gas over to the cold side. Okay, and then what happens then on the cold side, all the gas on the cold side, the cold side will get it to contract. So this hot gas on the cold side will reject heat to the cold side. And then again, as these pistons are moving along this axis, the axis is helping doing some of the work um, for the process. And so the axis has a specific design to it that allows this process to work as the gas is heated up, moved, cooled down, moved, heated up, etc. Anyways, Stirling cycle, it's the most difficult of them to kind of understand. But if I think just watch the YouTube video, it takes 1 minute, and you'll see a little bit how it works. We may only use it when we talk about solar concentrators. So there are systems where that could potentially be useful, but again, limited application. Here's a list of the various thermodynamic cycles. Again, the Rankine, Brayton cycle. These are important. Otto cycle also a useful cycle. Just talking about relative compression, heat addition, expansion, and heat rejection, and that's a measure of how efficient some of these processes can be. Other information. Let's see. I think I'm trying to wrap up here. So let's say, what do you want to do? So here's a pressure enthalpy diagram. Again, what's this one for? This is for a refrigerant. So we can go through refrigerate. We can talk about refrigeration processes as well. What am I working? Maybe this is a hint, or this is hopefully help for working on one of the homework problems. And in here we can look at what refrigeration cycle. So how do we go back and the refrigeration cycle is basically a heat pump. So we put in work in order to move heat from cold to hot, which would be like your AC and your refrigeration process. So let me just talk real quick about how we would do that. Whenever I treat AC systems or vapor compression cycles, which would be AC or refrigeration processes, I like to just start on the saturated vapor side. And this is going to be the material that goes into the compressor. So we first start by compressing. So I'm going to follow these constant entropy lines until I compress it. And I need to pick a temperature. I want to compress it to a temperature that I can exchange with my environment. So I need to be hotter. If I'm a refrigerator, I need to be hotter than room temperature. So I have to compress it to something that's hotter than room temperature. But I don't want to go too hot because then the hotter that I go, well, I'll mention that in a second. So anyways, I'm going to compress it to somewhere that's hotter. And I think right here, what this is looks like 70 degrees C. Here's the trade-off. Let's say I compress it to here. Okay, I know where I go, and then this is going to cool off. It's going to heat exchange with the ambient because the working fluid right here is going to be hotter than what would be the ambient in my house. Definitely less than 70 degrees Celsius, probably more like 25 degrees Celsius. So as my fluid transfers heat to my house, it's going to condense to, what is it? A saturated liquid. And then it might keep cooling until, again, where am I cooling it to? 60 degrees. At some point it can't keep cooling because it'll be the same temperature of the house. But once your difference, the yeah, so it cools to a saturated liquid or a cooled liquid. And then this liquid right here is sent through a throttle. When we send a liquid through a throttle, some of it vaporizes. So constant enthalpy process, delta H is 0 through the throttle until we get back down to the bottom pressure that we started at. So I'm going to throttle it to the pressure that I fed into the evaporator. And so some of the liquid will evaporate. So this will be liquid and vapor right here. And then this is colder than the inside of the temperature or inside of the refrigerator. So then, or we can consider AC, so colder than inside of the house. And so this is going to be what's used to pull heat out of the house or pull heat out of the refrigerator as it evaporates to a saturated vapor. I went through that a little bit quickly, but that sort of gives a little bit of an idea about how to use. I wanted to give you some ideas about how to use these pressure enthalpy diagrams to treat things like the Rankine process for electricity generation, or to do the reverse, which is put work in to move heat from cold to hot. So I think that's what I have for today, for this lecture. And yeah, um, just spend a little bit of time and touch up on your thermodynamics. These will be useful or important as we go through different things in this course.